So this is going to be, I thought of opening with the line and now for something completely different, because this is going to be not the big picture we just heard from Joseph, but this is going to be more talking about a particular package that's in development. And the kind of story here, I think, is something of the accidental engineer. I went to use a package that I liked and worked very well, and then when I went to use it at larger sample sizes, I encountered pretty serious memory problems and crashes, and so I really dug in to this technique and hopefully made some advances. Okay. So today I'm going to be talking about a particular kind of kernel regression called kernel regularized least squares. It's been getting a lot of attention in the social scientists. A lot of people who do econometric kind of research, regression discontinuity design, and that sort of thing, like to do a kernel regression. So I'm going to talk a little bit about why I like this particular technique. Then I'm going to give an example with a kind of fun toy little example where we talk about a field experiment where people are trying to maximize voter turnout in Michigan, and we're going to talk about how there was some treatment effect heterogeneity in spite of the randomization and how this technique can help you uncover that. And then finally, I'm going to talk about what me and Rob Schaefer have done, which is adapt a whole bunch of big packages, big memory, big analytics, big algebra, as well as RCPP to get C++ kind of boosts for speed. And so hopefully we have, big and fast as the goal. So the idea here, as with many non-parametric techniques, is to maximize inference while minimizing the amount of assumptions that we need to make. Any sort of approach when we try to learn from data is going to involve some sort of assumptions about where the data come from and how it might relate to the quantities that we really care about, whether that's a mean or a slope or any other kind of effect. Non-parametrics in general, for those of you who don't typically work with them, don't assume that the data speak directly to the unknown parameter that we're interested in. So you want to instead, say, looking simply at the data, you might look at the ranks of the data. You might in some way look at something that is harder to be tampered with and that is easier to understand where, in fact, those summary statistics do come from. This particular version of kernel regularized least squares, this particular version of the regression is nice in part because we're going to get estimates not only of the slope, the average marginal effect of some variable we may care about. We're also going to get an estimate of what some people call pairwise derivatives. I'm calling here local derivatives. But we're going to be able to estimate the slope at every single point in the data set. So it's very rich. If we have a nice and well-behaved data set, if one variable goes up, some other variable might go up, or it might go down, or it might stay the same. But in the real world, we often have very, very messy data sets where we have complicated curves. This approach is great for helping us map out the peaks and valleys, the hills and the mountains, so to speak, of the data set. One danger of this type of approach in general is overfitting the data, getting too excited about those curves when really the particular things don't matter and it's just something about the sampling process. So we're going to use something called regularization that's going to prevent overfitting, that's going to give a certain amount of smoothing out of those curves. And so there's going to be basically a weighted average of the messiness we see in the data with our need to make sense of that data and have smooth curves that we can interpret. It's a very nice paper that I recommend, Heimel and Hazlitt. They give some proofs as to why this kind of stuff works, as well as the original R algorithm that I'm going to be working from and hopefully improving with Rob. As the final bullet point hints at, this is a very interesting and kind of promising approach, but it's super RAM intensive. For a couple of different reasons, we get stuck working with n by n matrices, which get huge. Typically, just to do a quick comparison to the bread and butter kind of regression that we all learned the first time we learned regression of ordinary least squares, in that setup, if you have a matrix X that has n observations and let's say d independent variables, you wind up multiplying the matrices in such a way that you really collapse it. You collapse it into a D by D matrix. And for the most part, you have way more observations than you do explanatory variables, and so you're able to really shrink that matrix quite small. Well, this is the opposite approach. We're going to do all of our matrix multiplication in such a way that we're going to be stuck with that massive matrix, which is n by n. Now, of course, in theory, if you have lots of explanatory variables, other types of regression could approximate this. But the challenge here that we're really going to try to tackle head on is this scenario when we have these large square matrices where the size of each matrix is the number of observations squared multiplied by whatever the size of the float is in bytes. This space bar. So here's a really kind of rough schematic of the overview. We are going to set up y as our dependent variable, just like is typical. And we're going to say that y equals k, which is going to be a kernel that I'll talk a little bit more about in a moment, but kernel multiplied by a vector of weights c. The idea is that ultimately the kernel is going to tell us how similar each observation is to each other observation, and c is going to tell us how important each observation is. So if we have a lot of important observations that are really central to our data set, and they're very similar to each other, hopefully that's going to give us a nice clean prediction of the outcome y. Conversely, if we have these kind of really peripheral observations, maybe you do a whole sample of the United States, and there's, Hawaii is such a small state, only 3 people from Hawaii are included in the survey. And so you don't really learn anything about Hawaii one way or the other. And so you would want to say that we're not really making an inference about Hawaii at all. We're making an observation about, say, the continental United States. You'd want some way of downweighting the unimportant observations and some way of upweighting the things that are central to the thing that you're trying to investigate. So that's what K and C are. And you can choose K to be lots of different kernels depending on the problem and the particular properties that you want to optimize. Today I'm going to talk about a Gaussian kernel, which is nice. It's pretty easy to interpret. It does have the problem as being big. It's another one of these n by n matrices that we're going to have to worry about. And again, C is this vector of weights. So this is Gaussian in the sense that this looks an awful lot like what happens when we have a probability distribution that's normal. If you had the 2 there, it would look identical to the typical setup. But all we're doing here is looking at the Euclidean distance between each observation, and then we're going to use that to build similarity metric out of that. So if we have 2 people, I and J, 3 variables, age, income, and what did I say 3 was? Education. We're going to look at the difference, assuming that we have continuous measures of each of these. The difference between each of them, we're going to square it because we don't care about in which way they're different for the purpose of constructing the kernel. And then we'll have this nice measure. This bar is a nuisance. I used Sundown instead of Pandoc, and so ignore the bar. So we'll get that, and of course, so if distance is of course going to be between 0 and positive infinity. Therefore, if we set up the kernel like this with negative distance, we'll have this metric of similarity ranging from when distance is 0, similarity is 1, and then going on down from there. And then sigma squared here is actually something called the bandwidth. We get to choose how quickly we want this slope to go down or not, how quickly we want our observations to become 0 or not in the kernel. Here's a rough sketch of the algorithm. First, we just calculate the kernel. Second, we're going to get the eigenvectors and values, the eigenfunctions of the kernel. I'm going to talk more about that later, but getting the eigenfunctions, as always, is super computationally intensive, as I'm sure lots of people have run into here as well. The third step is to estimate how much regularization we're going to do, which without worrying too much about the details, we're basically, if you haven't done this kind of thing before, I would interpret the regularization parameter as a little bit like the null hypothesis that something's not true, it's just coming from the data somehow. And we're going to estimate numerically how much we want to say that maybe this stuff is just kind of an arbitrary pattern versus we're learning a lot from the kernel, we're learning a lot from our estimate of the weights. So the way that you actually estimate the parameter, it's an inequality based on the eigenvalues, but there's just a loop that goes through and finds something that finds the appropriate number in effect. So we get the weights then, and all this stuff is kind of cumulative. Once we get these things, we kind of use them again later. But we're able to get the weights next, and then of course predicted values as usual. And then here's this extra step that's pretty nifty. Not only are we able to predict the matrix, or the observations rather, y based on k and c, we're also able to get these local derivatives. We're also able to estimate the derivative at each point in our data set. And so that's super, super awesome and super interesting. It is slow, of course. It's memory intensive. And just to point out, one place where it's extra memory intensive is going to be for the scenario of binary variables, where we're actually estimating first differences. In that case, we're actually going to construct like a mega matrix that involves not only x, everything that we've observed, but imagine everybody got the treatment and everybody didn't. So you're going to have something that's actually 3x by 3x that we're going to have to play with to get our estimates in the case of binary variables, such as any categorical variable or treatment. And so to maintain this richness, the memory intensity is just going to keep going up and up. And of course, there are going to be a few different, also n by n variance matrices that we're going to have to worry about. Just to give a little sense of how the code works here, and this is in base R before, and I'll talk later about what it looks like when we switch over to some of those big packages. But if we have our typical matrix X with all of our observations, we're going to do the derivatives one column at a time. And in addition to some of those things I've already talked about, so the kernel is unsigned, right? It can only take positive values or 0. We want some measure of distance that is signed so that we can actually say which way things are flowing. So we're going to take the dth column of x, and we're going to use apply. And then once we use apply with this little function, this is actually going to return yet another n by n matrix. So we have this n by n distance matrix. We're going to do regular, not matrix multiplication on our kernel. And then finally, we're going to take our weights, C. And so now we've combined this information about distance, the kernel, and the weights to get an estimate of the derivative up to the constants. Can't forget about the constants. But we're able to get this derivative matrix, which has many rows as you have observations. So this nice rich matrix of how things are changing or not. Okay, here's an example. This one's fun. Particularly if you like social psychology kind of stuff. This is a funny thing that Andrew Gelman, some of you guys know, the big famous Bayesian, Andrew Gelman and some of his political science co-authors, as well as a political consultant, did this back in 2006. They were really interested in this question of why people vote or don't vote. And they wanted to see if one of the things that made people vote was perhaps social pressure, just a little bit of social pressure. And so they designed this experiment where they sent people a bunch of junk by mail. We've all gotten a lot of stuff by mail. But they very carefully randomized what type of message people got, 180,000 people in Michigan. And we're going to look at one particular scenario where 5,000 people got this neighbor's pressure treatment compared to a control group of 24,000. By the way, I should have said it to the beginning. I've got all these slides up, and all of these things are links, so I don't have to worry about jotting things down. But this is an example of the treatment. What if your neighbors knew whether you voted? It's public record. We've been talking about this forever. And this is, these aren't real names here, but this is actually what you would get, and these would actually be your neighbors' names. August was the 2004 primary. November was, of course, the presidential election where Bush won against Kerry, and see it's really high, but lots of people sit out the primaries. This person sat out the presidential, and they even say they're going to send out another one of these next time around. So in terms of designing an experiment that pressures people that IRB will sign off on, this is pretty good. Yeah, let's just go look at I just put together this super toy model to see whether it works. Does the pressure work using the kernel regression? And yes, it does. 10% increase in voter turnout. And you see age isn't statistically significant, but this is actually a variable that in both of those papers I mentioned, everyone's really concerned about age. You could imagine young people, they don't vote very much at all, and they certainly don't read the mail very much. So you might imagine that the effect just isn't really going to work on young people. You can imagine as people are getting older, they're more set in their ways, and maybe it's not going to have as large an effect. Well, either they vote or they don't, but their decision is not going to be made on a random piece of mail. So earlier approaches fit really complicated models with age and age squared and age cubed and age to the fourth multiplied by the treatment effect at each iteration of the polynomial. And this kind of really complicated models, the kind of thing nobody believes, even if your name is Gerber, it doesn't make sense. And so could we have a simple approach where we figure out what the treatment effect is without having to specify this in advance? And it turns out we can. And so this is using the kernel approach. We've gotten an estimate of the derivatives at every single age in the sample from 20 up to 100. And you see this kind of story. There's a big effect on people around 50 or 60, who knows why. But there's almost no effect on people who are young or old. And so the treatment effect is actually quite heterogeneous, and whatever is going on with the full story, this is not something random. If age wasn't part of the story, this line would be completely flat, right? But it's clearly not flat, so clearly we're having a different effect on age. So if you were a researcher, and maybe you hadn't thought too much about age one way or another when you designed your experiment, this would give you a great picture of how robust your findings are. Suppose you wanted to do this again, you might have really good confidence for people who are age, 40 to 70 or something like this, but you might not even want to bother with other groups of people there. The other thing you can do with this type of finding, I'm not going to talk about this step here, but you can use this as the first step of a regression discontinuity design, RDD, excuse me, which is a certain type of two-step regression where you understand some process and then you really zoom in on people who are near the tipping point, and you do a different test for people who are, in this case, right at the top of the hill. And you can see whether you have an effect on people who are a very similar age in this case. And so that might be another kind of test that you might want to do on a narrow group. Okay, so now to talk more about these memory challenges that we ran into here. So we have here plotted out, the y-axis is gigabytes, the x-axis is the number of observations. And if we square that number of observations and multiply by the number of bytes found in a typical float, we see how bad the problem can get. Right around when you get to 12,000, each one of these matrices is going to be a gigabyte. And then by the time we get to 25,000, each one of these is going to be 4 gigabytes. And so you're going to start hitting problems not only in terms of to some extent you can fix this with parallelization, but at some point, if you want things to run fast, you want them all to be on the same computer so that the matrix multiplication can happen. And at some point, when we're not even talking about particularly large data sets, you're gonna hit limits for a lot of systems. particularly if you're an ordinary user, not someone who has access to or know-how for more extensive computing systems. Okay, a little bit more specifics about the memory challenge. Just to give a sense, we are playing with a lot of these really large matrices. The eigenvectors, of course. The kernel is also big and slow and hard to get. Even though the kernel is symmetric, by the way, because it's a measure of the similarity between two people. So Joseph and I each have a score in the kernel, but it's the same whether it's Joseph versus me or me versus Joseph. So we can save a little bit and only do one triangle on the kernel, but it's still, at the end of the day, it's going to be a big thing that we need to multiply other things by. Those distance matrices, for each independent variable, we're going to have to create a distance matrix and do some of that stuff, and then the variance-covariance matrices. And then it's even worse, as I hinted there, it's even worse when you have binary variables. You have to create this massive 9n squared total number of entries matrix. Some good news. We don't need to invert any large matrices. In fact, we don't need to do any matrix inversion at all for this algorithm. So that is something that, like finding the eigenvectors, is just tough. Kernels are symmetric. We actually want the eigenvectors of the kernel, and whenever you're getting the eigenvectors of something that's symmetric, it's faster if you just set up the computer to know that that's what you're doing, and you pick an algorithm that appreciates the symmetry, basically. And there's another thing that is typically faster for computers, and that is we get to, in some cases, multiply things by a transpose, and in some cases, even the own transpose of that matrix. And just to give an example of how this works, of course, here we have matrix multiplication. Here we have multiplying something by its own transpose using that particular operator versus this nifty R function of crosspod, which we all know is faster. And just on a random matrix of 1,000 rows that's square, at this particular iteration, I just got that it was 2.5 times faster to use crossprod. So whenever we can use crossprod, that's going to give us a bit of a speed boost as well. Bad news, more, of course. Of course, as a reminder, the eigenvectors, that's bad. And we don't have, or at least we didn't find initially, we ended up just writing something, but we didn't have a big implementation of crossprod. And so Rob wound up writing one of those. Maybe there's a better one out there that we'll have to go and find. But that was nifty. OK, so here's what we did. Here's what is kind of the brand new thing to us. We have a package going now that we're going to call bigKRLS. And it's done a few things. First, we've reduced the peak memory needs. For the hard case of when you need to get part of the kernel for that giant binary Franken matrix, down to 9n squared. When we got our hands on this algorithm, it was closer to 16n squared multiplied by the number of independent variables. And so that was, well, we've done better than that. We've used these three packages. The authors' names are escaping me, but it's actually a similar group here. We wind up using big memory to handle the large matrices. We use big analytics does useful things like you can use the apply function, for example, from that. We use big algebra, but we actually don't do most of our linear algebra with big algebra. We do an awful lot of the linear algebra with RCPP Armadillo. Dirk was already mentioned earlier this evening. This is one of his collaborations. I'm not sure how much further we're going to go using Snow, but we have written an option. If you're comfortable with the size of the matrix on each of the different computers that you're using, then Snow will help you with speed, particularly if you have a large number of independent variables. Just to contrast, this is the same, or this is the analog to the code matrix, the code that we saw earlier. Because we're using big analytics, we get to use apply just like before, get this n by n matrix. The element-wise multiplication, that's written in C++ in effect, using Armadillo to get there. Then we have this thing here, the weights. The weights are, of course, an n by 1 vector. So they're by themselves not that big, but we're going to need to multiply them by a big matrix. So it's better to coerce it into a big matrix and have them do their multiplication. But then the derivative matrix itself is not that big, and you don't need to do anything to the derivative matrix once you've got the estimates that is particularly intensive. So we coerce it back into a regular R base R matrix. We have a few speed tests, and then we're about out of time, I'm sure. We've done two rounds. This is comparing the initial algorithm that Heimerl and Hazlitt wrote to what we've written. We're in red, and the other one's in blue. And this is the average of 100 simulations. Over here, we have the matrix size. And this is like literally hot off the press, so it's only going up to 4,000 here. But you see, we have at least some speed gains in most scenarios, with the exception of like a kind of near tie here on or even slightly slower on cross prod. But we're making using this kind of cluster of packages, we're able to get the kernel much faster as it starts to get big, and we're able to get the eigenvectors much faster. So that's a promising first test. This is comparing a little bit more of an apples-to-apples comparison. This is comparing our algorithm cleaned up memorized as best as we possibly could, using the big R stuff versus not using the big R stuff. And the time, so the higher it is, the longer it takes, is our y-axis. You see that particularly when you look over here at the largest matrix, we've tested it on the 5,000 square one, the big RCPP stuff, plus big algebra and big memory, this is markedly faster than using base R. So we're seeing initial signs of speed boosts, basically. Next steps, we can actually repeat step 1 after each step. Step 2, as some of you probably know, you don't necessarily need all of the eigenvectors. You can actually choose some portion of them. So we're going to choose an appropriate method for picking the eigenvectors that we want. We have to be careful because those eigenvalues are also used for the data regularization parameter lambda, but so we may be able to get some speed gains by not getting the whole eigenvector matrix, but we're certainly going to want to do some tests and some simulations to make sure we're not losing too much either. Because of the fact, I just had that one little graph up, but I think with all the derivatives, I think data visualization is paramount for a technique like this to really learn as much as you can. So one next step that we're excited about is doing a Shiny app so that typical users, without a whole lot of fuss, can start really interacting with the results. Of course, we might want to look for similar techniques, particularly some of the stuff like found in the MP package, to see if our code or our approach is helpful there as well for similar problems. And Rob and I have a kind of spin-off paper going as well that's a little bit more substantive in the context of the political science research that we do, but just to see how this type of approach compares with similar methods and models. Okay. That is it. As I said, this is brand new. The code it won't even be up for a few days, but I'd love to hear any thoughts, as I'm sure would Rob. So thank you very much for your attention and your time.
All right, before we let him go, do we have any questions? I see a few hands up there in the front.
I think we got one here.
We got one.
So how sensitive is the algorithm to the choice of kernel?
So we haven't, we've actually just been treating the Gaussian as a given for the time being. I suspect it will be at least somewhat sensitive, but that's a downstream problem right now. So. Ask me over after the summer, I would say.